Hi, my name is Linnea.
I'm Bezia.
And I'm Linnea, and this is episode number 22 of the Lemma Journal Club.
What is the Lemma Journal Club?
The Lemma Journal Club is the show where we read every paper to tell you if you need to read it. You probably do.
We have a terrific paper for you today. We are talking about oxygen depletion in biomolecular condensates is dominated by macromolecular density by a bunch of people from Aarhus. Again, not from our house, from Aarhus, Denmark.
So, Bezia, why did you pick this paper?
We've been doing little Lemma Journal Club weekly updates in which we say all the papers that were published in biophysics broadly speaking in the past week. We've done it for 3 weeks now. It's not good. It's not fun to watch. It's not fun to make. But it is an interesting task, which exposes me to a lot of papers that I'm not normally seeing from my friends or from my Google Scholar updates or from my PubMed updates or anything. This is one of the papers that got pulled. We don't know anybody on it. It is interesting. We've done another Aarhus, Denmark paper about oxygen sensing via the same probe. This paper about oxygen sensing in the avian eye.
Okay.
They use the same technique. That is our least watched podcast that we've ever made. It has 10 listens total, 2 of which are me. So that was not appreciated, which I'm surprised by because I thought it was a really cool story. I picked this paper thinking, it's biomolecular condensates, which is you, and it's oxygen depletion, which is me. And this will be a great paper to do the overlap of the two of us. And this paper was a emotional roller coaster. I got about 3 paragraphs into it, and I was like, this was a huge mistake. And I tried to wiggle out of it and do another paper. And you were like, no, I've already read the paper. We have to do this. And I'm super glad that happened because this ended up being a tremendous paper. There's a lot of parts about this paper that are very difficult, but
I found this a really difficult paper to get through and to believe that they are really pulling out. I think they're at the limit of the things that you can really measure about a system.
I think that they are clearly past that limit.
Really, what does that mean?
That the measurements that they are making are not
real.
Well, right, like the data that they collect is real.
Sure.
And the data that they collect is very exciting. Their molecular dynamic simulations do not match the data that they collect. And they say that pretty proudly. Hey, we worked very hard to simulate this and we don't get the same result. So something is up. That's great. Their pinning of units onto a measurement that is not actually coming out as units by making certain assumptions, I fundamentally disagree with the assumptions. And Keeley, they make this assumption where they're trying to do units, which is that the diffusion in the dense and the dilute phase for oxygen is the same, that the diffusion constant for oxygen is the same. And I think that not only is that not correct, but the diffusion constant changing for oxygen between the dense and the dilute phase is the whole ball game. That's going to be how this thing is falling out. And so by ignoring that to try to get themselves units of micromolars from their PLIM experiments, they've gone in the wrong direction.
Interesting.
That being said, it's admirable to try something. They've tried some measurements, which have a tremendous amount of problems with the measurements. But again, they've tried something. Yeah. It's admirable to try something. And I find at the end of the day, this paper is super exciting. I also will say, I think we're far enough into the recording now. This killed me.
The thing that killed me was monotonous.
Monotonous and repetitive. They kept saying the same sentences.
No. Like they used the word monotonous.
Oh, they used the word monotonous literally.
Instead of monotonic. Something is monotonously increasing.
Look at that.
And they do it multiple times.
I just replaced it in my head with monotonic. It is monotonously. Yeah. It's also monotonously written.
Monotonously. Yeah.
I think they describe certain things like how PLIM works. Let's see. I'm just going to do a control F for triplet. The phosphorescent dye is quenched by the triplet state of molecular oxygen, and the lifetime thus decreases with increasing oxygen concentration. They say something along these lines 5 times in this paper, where they describe over and over again this singlet excited state to triplet excited state piece of information that you absolutely do not need in this paper. And it's just like to me, it was the strongest symptom of something that was going on, where it was useful information was continuously mixed in with unuseful information. And I don't necessarily agree with this concept in papers that you can only say one thing once. Like, it is sometimes nice to say it again.
Yeah.
But you should not say it 3 times. You certainly shouldn't be saying it 5 times.
Yeah, it was really hard to get to the meat of the paper, I felt.
Yeah. This was received May 3rd, 2024.
Yeah.
It was accepted January 30th, 2026.
Yeah, God.
And presumably they did not submit to Nature Communications initially. Presumably this was like a 4-year review process for this paper.
Yeah.
In addition to that, they have put it up. It's published February 10th, 2026. But they say, Nature Communications say, we are providing an unedited version of this manuscript to give early access to its findings. Before final publication, the manuscript will undergo further editing. They've published it in a way where every single page, across the diagonal of the page, it says in giant letters, article in press, which makes it really hard to highlight anything and kind of annoying to read. And then, even though it's published, but not really published, whatever the heck that means, we have this problem of all the figures are jammed at the bottom of the manuscript, and they're all kind of weird sizes and stuff like this. We encountered this a little bit in episode 3 when we did the mitochondria purling paper, where again, they published it. But that time I understood. I knew that there were a couple groups working on the same thing. Different groups maybe were racing to get certain things out. And so they really wanted this to come out quickly. Here, no way that anybody else is working on this. There was no reason that this was like a time-sensitive, needs to get published right now, this moment kind of thing. Why do this?
Well, it could have been for somebody's, like, we don't know what the authors, like, it could have been one of the authors pushed for this because of their careers, that they needed it so that other people could read it and access it, and they didn't want to preprint it for some reason.
Yeah, I have no doubt that this paper has, like, destroyed Ankush Garg's, the first author's, career just by taking so long to publish it. But we've talked about this before. An accepted paper is just as good as a published paper. There's no need for the career to have this, like...
Well, if people can't read the paper, we didn't find a preprint of this paper, right?
Oh, that's true.
So the only way that they can read it is through the journal.
That's true. And at some point, they're not allowed to put up a preprint anymore.
Yeah,
that's
especially
a good point.
with like Nature Communications, which is a pretty
there is
predatory.
A preprint of this paper.
Oh, yeah. Okay.
October 9th, 2024.
Okay.
That's
Wow.
a long time to get this paper published.
Yeah. One hopes that there was something exciting in between.
Papers ReadCube, the thing that I use to read papers, has updated its interface. And at first I thought I could bring it back. I can't bring it back. I'm stuck with the new interface. The new interface has an interesting, I'm going to call it glitch, where if I'm trying to add sticky notes to make comments about what I want to talk to about this paper, every time I click anywhere on the manuscript, it creates a new sticky note. And if I try to like delete or something, that just creates another new sticky note. Every interaction creates another new sticky note until I click away from the sticky note tool. And so I have littered this document with empty sticky notes because Papers ReadCube, their interface is a mess. Please God, change it back. I'm just walking through my notes of different things that I tried for this paper.
Yeah. I mean, I think the coolest thing I found about this paper was the PLIM.
Yeah.
Right. I think this is a very cool idea and like a very cool way to try to make these kinds of measurements.
And I was not really aware of it. I knew about the gold sensors. I knew about the gold sensors before the last paper that we covered that used them. I was not really aware of this idea of, hey, let's have something that has an incredibly long lifetime, but an interaction with oxygen that truncates its lifetime. Mm-hmm. And then we can see the interaction of that fluorophore with oxygen, and we can guess the oxygen's concentration via that truncated lifetime.
Yeah, well, one of the caveats that they mentioned in the discussion is that it really does need good controls and good, they were saying like tau zero, essentially. And so they didn't know whether it was like actually applicable to biological systems. I can't remember, like they didn't do microscopy. They didn't do PLIM in the Anoxiest eye paper, right?
No.
They did this electrode thing.
Yeah.
And so Yeah.
And
so
in
how?
the Anoxiest I thing, they did the electrode thing, but they were not able to get units of micromolar.
Right.
Because they could not make assumptions about the physics, essentially. I think.
But I think even in this in vitro system, I'm not convinced by the assumptions. And so to get real units, I think you could get relative measurements in a biological system, which would be cool. But I'm not sure you can get real units.
Right. So what they need is to get concentration. Concentration is equal to the solubility coefficient of a liquid times the partial pressure of the oxygen. Mm-hmm. So the probe measures the partial pressure of the oxygen. In the Anoxiest I episode, 2 episodes ago, only 8 people have watched it. Please listen to it. Watch or listen, I don't know. In the Anoxiest I, they didn't know the solubility coefficient of the liquid because it's a bunch of liquids. And so here they say we can get concentration because we think we know the solubility coefficient of the dilute phase, and we think we know it of the dense phase. And so we can calculate it from an equation. I think that clearly falls apart. I think they probably think that clearly falls apart because, again, they're seeing things that are not captured by theory, and they don't have a great explanation for that. But the idea that there is a pretty nice relationship between concentration and partial pressure.
Yeah.
And that you can work away at getting that solubility coefficient makes me think that you can work away at getting units in a tissue via this method.
Yeah, I don't know because...
Well, I guess that I just said all of that, but I said all of that for partial pressure for the probe. That's not what's going on with the PLIM. PLIM, by the way, terrible word.
Oh, yeah. I thought it was cute because of phlegm.
Yeah, sure. But phlegm sounds like, science. PLIM sounds like, I don't know, some weird cooking term. I don't know what PLIM is, but it's not great. Yeah, I guess for the PLIM, yeah, as you said, you need this tau naught, so it's harder to work away. But they do say, hey, maybe you could get a fluorophore where it's less dependent on tau naught, and you could start to get closer and closer to
Yeah, they do suggest some, but it does seem like that's a whole nother tech development step.
Yeah.
And that even in this controlled system, I wasn't super convinced about the micromolar measurements because so much can be changing just between the dense and dilute phase of condensate. So like, if you go into an organism and you're trying to compare different subcompartments.
But what you can see, right, is you can see spatial patterning.
Yeah, I agree with that.
Of the oxygen concentrations.
But is that true? I agree you can see spatial patterning of the dye.
I see. But
it could be lifetimes.
It could be patterning, yeah.
But it could be due to the microenvironment and not actually be the oxygen.
People do this argument all the time about pH sensitive dyes where they're like, oh, the dye is pH sensitive. pH changes quite a lot within a single cell. So are you really measuring changes in concentration of whatever your dye is supposed to be, or are you just looking at pH?
Yeah.
But like the pH, the full swing of pH in a cells for a lot of these dyes is like a 1% change in dye fluorescence intensity. And so like all you have to show here is that really big swings in parameters are not making your oxygen density change by twofold. They're making it change by like 5% or something.
Yeah.
And then you're in business again. You can say, I know like once it becomes a big enough gradient, I know that that's real.
Okay.
And maybe you can't. Maybe that's a limitation.
Well, I actually think that that is part of the reason why I found the conversion to real units unconvincing is that if you look at these changes in intensity, they look very small. Yeah,
so why do you think that they felt that they needed to go to units? I think it's admirable to try.
Yeah.
But also I frequently don't try because it is so weak. So I do it for myself, but I don't put it in, I measured ATP concentration for myself for my system and how it's changing. I didn't put it in the paper because I felt it was very weak. Yeah, why do you think that they felt they had to do a real unit rather than relative concentration or something?
Yeah, it's a good question. I'm not totally sure. I'm not up on the literature in this subfield of oxygen sensing. So maybe relative concentrations are already probable.
But I think that this is a novel thing that there exists less oxygen inside the dense phase of the condensates.
Yeah.
And you say that the microscopy is not that convincing. I just want to point out that the microscopy is FLIM. And so like how convincing it is largely a function of the way that they choose to present the images. So they've chosen to present the images with a very limited rescaling, where they're just going to show you all the way from 0 nanoseconds to 1,000 nanoseconds in a single image. They could have auto-contrasted this.
Yeah.
And it would have been much more convincing.
Yeah.
Yeah, that with FLIM, you get a lot of choice on how you present the quality of your data.
Yeah.
These are not graphically minded people. These are not communication minded people.
Yeah, these are
scientists.
these are yeah.
This is old school scientists, chemists, biologists. I mean, these are salt of the earth. I mean, all this is salt of the earth. This to me screams like NYU Brandeis style science.
Yeah, I mean, I thought this was like some of the things I really liked about the paper was that they were comparing a lot of their PLIM, this new measurement, this PLIM measurement, to kind of the old school electrode measurements. And I thought that was really helpful with trusting or extracting real information from the new technique.
But there isn't one thing is we should say for new technique. I was trying to figure out how new this technique is, right? Because I didn't know about it. There is a paper doing a spatial picture of tissue using PLIM on lymph node slices.
Oh, okay.
In 2024.
Okay.
So yeah, from the way they wrote it, it was hard for me to understand how much they had developed and how much already existed. It was pretty clear that the probe already existed and that many variations of the probes already existed. And so maybe what was developed here was some of the math around analyzing it and trying to bring it into units.
Yeah.
To me, the big finding here is not the math or the analytical techniques, but the fact that these condensates have a different oxygen concentration.
But I think that all of the math and analytical techniques are necessary to be able to say that. Because otherwise, this lifetime could be changing for a huge number of reasons.
I hear you. Yeah. It does seem, And then it's like, well, okay, let me ask you this then. Given the measurements, and there's no measurement that they do that really holds up, right? And they more or less say that, right? Given the measurements between the probe measurement, which is super sloppy, and the PLIM measurement, which has a lot of caveats, do you believe that the oxygen concentration inside the condensates is lower than the oxygen concentration outside the condensates?
Yeah, I'm still...
You're skeptical about it.
I am. I mean, it's probably a limitation in me and my understanding. And also, in the... I really wish the paper was written more digestibly because they run a lot of controls. So clearly they have been thinking very hard about. But I didn't understand all of the controls. And I put a lot of time into this paper, right? We were on the plane for 4 hours. I did not sleep at all. I read this paper the whole time trying to understand it. And so, but I was not sold that this was not an artifact due to the microenvironment.
If you have a dense condensate, then clearly that dense condensate is denser in many molecules, right? And so when I actually started reading the paper, I was like, oh, obviously oxygen is going to be in a higher concentration outside the condensates because the condensate is denser. There's more things that interact with the oxygen, so it's going to have a harder time diffusing into the condensate.
Yeah.
But clearly that's not true for all sorts of small things, that there's all sorts of small things that are enriched in the condensate. And so why are some things enriched in the condensate and other things not enriched in the condensate? And now you have to start thinking about these electronic interactions, and oxygen is nonpolar. Is there a polar, nonpolar thing? And they talk about this a lot. They try to do molecular dynamics to simulate it. They end up saying, we don't know, which is a great place to be.
Yeah.
But I did have to second guess that this was obviously true when I started. And as I thought about it more and more, I was like, oh, actually, I think flip a coin on whether or not I would assume that this is true. And then has their measurements changed? If my prior is now 50-50 after I thought about it a lot, has this changed my posterior? with the data that they've shown.
Yeah.
And I feel yes, but it's interesting to hear that you feel no, that it really hasn't really changed your posterior.
Well, I mean, I think I'm still intrigued by this idea, but I went into this paper being like, oh yeah, this is something people are thinking about, is like, how can the dense phase and dilute phase interact differently with small molecules? This is like Pedro D'Souza's whole.
Yeah. This is just something I haven't thought about, but yeah.
Yeah. But, and so I went in thinking, oh, okay, so yeah, this is possible. And I've left being like, okay, yeah, it's possible, right? Like, I think that their probe measurement in figure 1, like with the bulk separation, is like, okay, like
it's very strong, except for you look at the picture, and they showed the picture, which is very brave of them, because if they hadn't shown the picture, I would have thought it was a much more powerful measurement than it is. Although I suspected, just from reading the text, I suspected, and then I looked at the picture. They put that probe in, and it completely destroys the separation between the dense phase and the dilute phase. And it destroys it so much, you can see in the picture, I think it's I have to scroll all the way down to it, 1F. It destroys it so much that you can see in 1E, it actually creates a new time dependency of the oxygen concentration the probe is reading as it like recoarsens and the dense and dilute phase begin to mix and nucleate off of the probe and stuff like this.
Yeah.
I wonder if they could have made, rather than do it all in an Eppendorf tube as they show, if they could have made this like, in a cup or something, really get the dense and the dilute phase to be like macroscopic and then try again.
Yeah.
Yeah, there's a lot of caveats.
Or different
in every measurement that they do. Once we got into the molecular dynamics, they started to skim over what they were doing. Because again, it doesn't capture what they're experimentally seeing. I am surprised and thankful. Again, this paper came to us by this automated system we've made to try to get all the biophysics papers that exist and are published every week. The heaviest filter in that process is if you mention molecular dynamics in your abstract, you should really triple check that this is not just a molecular dynamics paper. And I'm surprised that this paper made it through that check. I mean, obviously it should have made it through that check, but like AI is not good at this stuff. And it does say molecular dynamics right in the abstract. And then about a third of the paper is about molecular dynamics. So surprised it made it through, very thankful that it made it through. Because again, I have a lot of inspiration on ways that I can do experiments now from this paper.
Yeah.
That I was already nucleating in my mind from the anoxic eye episode. I think that's episode 20. It might be episode 19. I have this list of experiments that I would like to do during my life. And I rank the list by like, what is the impact it would have on humanity? What is the impact it would have on science? What is the risk that it will work out? How long is it going to take? How expensive is it going to be? And I put all those together and come up for a ranking of, should this be the next experiment I do? And 2 more experiment ideas got added from this paper. It's rare. I would say only like 3 or 4 ideas get added to that list every year, because I really try to only add really good ideas. And so this was a very rich paper for me for coming up with ideas. It also changed a little bit my heuristic for how I'm ranking these ideas, because both of the ideas that came out of this they're quite high at the top of the list, but not beautiful. The resulting data will look ugly. And I realize that we've talked a lot in this podcast about our sense of scientific aesthetics. And so I added a new column, which is aesthetics. How beautiful is these experiments going to be? And these get a 2 on a ranking of 1 to 3. They'll be medium beauty, but there is a reshuffling of things based off of not only how important is it going to be and how risky is it going to be, but how, beautiful to me is it going to be.
Yeah. Talking about the risk or the cost, this requires a FLIM setup. So this is not accessible to most people. I mean, like, I guess if you have a FLIM in your core facility, you could do some pilot experiments.
Which Princeton does not, which is crazy to me.
But yeah, so it's not a super accessible technique. Yeah.
This is, I was saying before this, we have no options really of where to go next in our career. We have to go become professors now, and it's a really, really bad time to do that for us. But we have, hints of possible options. Some of our hints of possible options are places where we would have less resources, but be closer to family, and other places where we would have more resources, but be further from family. And while going through this paper, I got really excited about having more resources, because this requires Flim. And on my spreadsheet of ideas, this is not the top idea because the cost to this gets a 3. It's maximum cost. Or I think actually it gets a 1. That 1 is max because it's like worst. It's the worst possible cost. It requires really specialized equipment that I probably will not have access to in most places we could possibly go. This is like a superpower of like if you get your timing right, if you just get access to things early in your career, it totally changes the trajectory of what you can do in those first 5 to 10 years when you're really revving to go and thinking super creatively.
Yeah.
And it is kind of a pain that like the way it tends to go is you go to a smaller place initially, except for the like golden children. You prove yourself at the smaller place. And then when you're like 60 years old, you get to move to like Harvard or wherever. And then you get tremendous resources. But now you're also kind of a dinosaur. So why are they giving you tremendous resources?
Yeah.
I did like they say in this, talking about dinosaurs, in the introduction, they say, in addition to the traditional organelles, a new type of compartment has recently been identified that form by condensation of biomolecules, so-called biomolecular condensates, or membraneless organelles. To call this a new type of compartment, I mean, how long has it been now? 15 years? This is like saying a new gene editing technology named CRISPR in the introduction of your paper coming out this year. Except even more ridiculous, because I think CRISPR is more recent than biomolecular condensates.
Yeah, it's a common thing people say, so I wasn't shocked by it. Time passes quickly. 2009 was Cliff's first paper, the P granules paper.
Yeah, I feel like if it's not within the past decade, you can't call it a new thing anymore.
Yeah, but they wrote this paper in 2024, or probably they wrote the paper in 2023.
Sure. Still, 2019 was the last year that I was going to allow people to say a new thing that's been discovered about biomolecular condensates.
How about new relative to membrane-bound organelles?
Sure.
I'm surprised that you don't buy this assumption that the diffusion of oxygen is the same.
Yeah, so this is, I mean, I'm aware that most people would disagree with me on this. But what happened to me is I was like, ATP is a small molecule.
Yeah.
Right? And I spent, 5-6 years of my life working with ATP in aqueous solutions where I was making the solution. It wasn't really biology, and there were some biological components in that aqueous solution. And I was like, the diffusion coefficient of ATP in this aqueous solution is roughly 200 microns squared per second, and plus or minus a micron squared per second, right? That was pretty much the number, right?
Yeah.
Certainly not 20 microns squared per second. And I went into tissue biology making the same assumption. It's going to be 200 microns squared per second in any sort of cell that I look at. Well, in muscle cell, it can range between like 0.1 micron squared per second to like 10 to the negative 7th micron squared per second, right? Like the ATP can really get stuck in muscle cells.
Yeah.
And that's because these bundles form kind of like if the ATP is trying to diffuse through the bundles make a physical wall in the muscle cell that the ATP can't get through. And it's like trying to go through a size exclusion column or something like that.
Yeah.
Okay, so then I start to think about biology as an incredibly complicated active size exclusion column. And then I start to think about diffusion, but not just an incredibly complicated active size exclusion column, but one with many weird binding properties. So everything in the cell sometimes is kind of pushing the ATP away or glomming onto the ATP, and the ATP is forced to interact with a lot of things on its diffusion route.
Yeah.
And so what you end up getting from the few people who have tried to measure it is a diffusion coefficient that looks more like 100 microns squared per second. And it's this oil-Millikan drop thing. So I'll just briefly, for our listeners, talk about oil-Millikan drop. You know this story.
Yep.
But this is a great story in physics of when they were first trying to measure the charge of the electron. This guy, Millikan, made a experiment in which you drop little bits of oil next to a known charge and watch the oil droplets deflection towards the charge as it's dropping. And from that, you can calculate the charge of the electron. And he writes down a measurement, and then someone else repeats the measurement, and they get a slightly different number, or they publish that they get a slightly different number. And then someone else repeats the measurement, and they publish that they get a slightly different number. And for the next 10, 20 years, that number slowly drifts from Millikan's first number to a completely different number, and then they finally get the right charge of an electron. But everyone was so scared of disagreeing with previous literature that they just kept fudging their numbers towards the right direction. And they just herded, and it took a tremendous amount of careers for us to finally get the right number because scientists are so afraid of saying something new. And also, it's so hard to say something new. If the next publication is like, this person got it wrong, it's actually this number, that'll take you 20 years to publish. Better to publish 20 papers and change the number a little bit each time. So I think that a similar thing is happening for the diffusion coefficient of small molecules in cells. That we're originally like 200 microns squared per second of ATP in an aqueous solution. It's going to be roughly the same in cell. So I think it's going to drop down to 10 microns squared per second.
Sure.
Over the next 5 years as people continuously measure it.
Just to push back on this a little bit, like I think that this is absolutely valid in a biological system where there's lots of things to be interacting with these small molecules. And yeah, like I think it applies not only to ATP but also to gases and
But this is
this is not a cell, right? The only things in this test tube are these peptides, these repeat peptides and some buffers. So you think that it's sufficient, like that oxygen, I think I think the assumption that's safe to make is that the diffusion coefficient of these small molecules is not changing due to the viscosity, due to these classic parameters that we think affect diffusion. That like if you were to measure the viscosity of the dense and dilute phase and then calculate out what the diffusion coefficient of oxygen would be in those two phases, it would be essentially the same. And so that any change in the diffusion coefficient is due to the interaction between oxygen and the peptide.
Sure. And I think they try to capture this in the molecular dynamics, and they don't successfully capture this in the molecular dynamics.
Yeah.
And so I'll say, I think that maybe the classical way of thinking about diffusion of oxygen in a polymer is for some reason breaking down in a polymer that's essentially a chain of amino acids. And that there's enough complex interactions happening with the amino acids that you can get some weird interactions of oxygen, or if we put in ATP into the system, would there be concentrations of ATP? And which way would it go? Would there be more ATP in the condensate or less? And that's why I said it's 50-50. And you could be right that there really is no oxygen difference because this is not real biology. And my thinking was that this is close enough to real biology that it's going to create these concentration changes, these gradients that I believe exist because I believe that there are diffusion coefficient differences in biology. And I was like, this is close enough. But it's a good point that you raise that maybe that this is not close enough to biology for this mindset that I have to be activating. I've just swung so hard the other way that I used to be like, the diffusion coefficient is A. And don't tell me otherwise because you're being silly. Now I'm swung all the way over to, you know who's back? You know who just flew up?
The hawk.
The hawk.
Yeah.
I talked about the hawk.
We've got to put you on the other side of the table.
Yeah, I talked about it in the other episode. It's such a weird dead space when I start talking about this hawk. And now we're going to have that dead space again because I'm just staring at this hawk. Look at him.
Yeah, the assumption about diffusion comes so early that I was surprised that you said that was where your like the assumption that broke down for you, and B, that you then believed any of the measurements in the paper.
Well, so to be clear, it came super early. I highlighted in red, and I was like, from now on, I do not trust the math that they're doing. I didn't say that I trust necessarily the units that they create, but I do trust the measurement.
Sure. Yeah, sorry, that was a misspoke.
Right.
Yeah.
And so that's the thing, is that they do show enough of what I would consider like the rawish data for me to think about the rawish data in my own schema and think about, I kind of think that there is really less oxygen in these droplets in my own schema.
Yeah. I mean, that's impressive. I mean, to both for on the writing side and the science side, that they've presented enough of the raw data and haven't skewed it by their interpretations and assumptions, and on your side for
salt of the earth people. These are real scientists, no flash, doing what they do. I do wonder, I didn't check if any of these scientists are the same scientists from the Anoxic Eye paper.
Yeah, I didn't remember where Anoxic came from.
It comes from the same place, and it's the same probe. So I wonder, like, is it literally physically the same probe?
Yeah, I bet yes. Right? I haven't read that many papers doing this oxygen.
I don't know how expensive the probe is. Yeah.
But yeah, I was intrigued by this paper as well. Like, and it was a good brainstorming paper, as you suggested for yourself, in terms of thinking about the pyrenoid and chlamydomonas and also in vitro reconstitution of it. So like one major thing that people haven't been able to measure in clammy is like where actually is the CO2. So the pyrenoid is supposed to be concentrating CO2 around rubisco, and all of our evidence so far suggests that that's true, but we have never actually seen that that's what's happening.
Yeah.
And so the idea that you can look at a small molecule inside of like either in vitro or in vivo and be able to actually measure these things is really exciting. And yeah, so that was something that I was thinking about. And if the condensate itself can be partitioning out these small molecules, right? This is something that is in the background, like Rohit Papu thinks about this kind of thing a lot, but it's not in the like day-to-day conversations that I'm having about condensates, and definitely not about the pyrenoid. And so could the pyrenoid, like the formation of the condensate itself, be excluding oxygen, which would be good for the pyrenoid, would be cool. And also, yeah, thinking about the evolutionary, anyways, it was a good brainstorming paper.
Well, I guess, yeah. But he brings up an interesting point that, like, let's say we like literally wanted to do these experiments for your in vitro system.
Yeah.
We don't have either of these sensors.
Well, so like it did, yeah. I don't think I would start with these experiments, right? I don't think I would start with oxygen. I think I would start with your experiments
of ATP. Yeah.
With all the caveats that they've brought up
Yeah.
Of like, okay, these are and that we've brought up just discussing.
Yeah, we've tried to do this a little bit.
We did this a little bit, and we did see a pattern, right?
Yeah.
And so like, but we had a lot of trouble interpreting that pattern.
Yeah.
And so going back to those experiments and thinking about would be very cool.
Yeah.
And then once we have our feet under us, like that would be moving on to the small molecules and would be very cool.
So in the end, it's one of my favorite papers that we've done.
It is a real, like, I know the weekly updates are bad, but like, they're good. They're
good. We
gotta find a way to make them good. I guess.
We've been doing this. I've been running a update in the background, although I see, it worked. I've been running an update in the background, so it's gotten the new papers from this week. And so right after this, we'll record another one, or maybe an hour after this, we'll record another one, which is this next week's papers. It's a bad format. People liked watching the last one, not because it's any better, but because it's recorded in Puerto Rico. We went to Puerto Rico for a few days. We got stuck there because of the blizzard, which was an interesting experience. People watched it because it was Puerto Rico.
Yeah.
And we talked about two papers in which they're doing like how the magnetic sensors in birds work. And one of them is in quail. And Jacob has a great comment, which is he says, "I'm not aware of any quail that can fly," which is a great, like, what are we talking about? Like, so obviously we're talking about something like evolutionarily in those papers, but it's a great comment of if you're using quail or chickens to study things that might have evolved from migratory birds, it's weird.
Yeah. Very vestigial.
A bird just pecked the hawk, and the hawk has flown away now. Some tiny bird came up to it and pecked it on its head.
Right. I've been seeing beautiful birds here. I was sitting here with Asya yesterday, and I saw like a blue jay. They look so beautiful in the snow, and a female cardinal, who are just like, those are my favorite birds to see. The little bit of red, but mostly brown.
I feel like they really come out to our property in particular in the snow. Then maybe it's something about how the chickens are getting their food, where the little birds are really like, this is the place to be.
Yeah.
I'll say one more thing that I have on my notes that I just want to talk about.
Sure.
Is Notebook LM. This is a Google large language model AI thing that creates podcasts from papers. Weird service. I've talked about this before, where people are like, we really want you to discuss the context of the paper and bring it down to a lower level and let us know what we're listening to and summarize the paper. And I'm like, nah, we have no interest in doing that. We've both read the paper. We're discussing the paper and talking how a real journal club feels like, so that people who are junior scientists or not in science can see what these conversations are like normally at a scientific journal club. I tried to use Notebook LM for this paper and for another paper to read me a paper as an audiobook. because I thought that that might be like a thing where I could like prompt it, say like, just read this to me as an audiobook. And I gave it some like specifics on how like, please read equations like this and read genetic stuff like this. It can't do that. That's not in its repertoire, which I'm surprised by. And so I ended up listening to a podcast summary of this paper and another paper from Notebook LM. And it's garbage. I had never really used it to try to do what I was saying. And it essentially tries to summarize it based off of the abstract and maybe the first paragraph. And so basically it makes a podcast off of this first paragraph and nothing else. And I was really surprised at how little it was able to talk about the actual paper or go into depth. And it does this AI thing where every single time it tries to explain a concept, it makes an analogy to another not necessarily analogous concept, where it's like, imagine that this is, a crowded stadium and these people are standing up and these people are sitting down, and they like just goes very heavy on imagine that A is B and B is C. And so Notebook LM, awful, F-. It pretends to cover the whole paper, but it doesn't actually work. I actually don't understand why Notebook LM exists, because you could never get any information from a paper that way. Like maybe it exists for children. It's certainly not marketed towards children though. So.
Yeah, we in Cliff's lab, we've been doing AI minutes at the beginning of every group meeting.
Yes.
And Anita, for her AI minutes, gave Notebook LM her paper and had said, like, make a 5-minute podcast. And we just listened, or like, and it also made like a visual, like a presentation. Cool. And so we like listened to this AI summary of her work, which we've been hearing about for the past, 4 years. So we're very familiar with. And you can really see like, when you're that close to the work, you can see where it like does okay and then where it just completely breaks down. But to use it as the way to digest something for the first time, it seems not.
Yeah, so I'm going to like backtrack what I was saying to people, which I've been saying, if you want some whitewashed podcast about science papers you haven't read, use Notebook LM. No, don't do that. I don't quite know what you do, to be honest. What I have been doing is I've been copying and pasting paragraphs from papers into a large language model and saying, can you please read this out loud to me? There is no automated summary of papers. We will continue to shout out other podcasts that cover papers in an interesting way.
Yeah.
So I guess another shout out here it's called Plants and Pipettes.
Plants and Pipettes does, but it's not summarizing papers.
Sure.
But the other thing to do if you want a summary of a paper would be to put the title into YouTube and see if these people have given a talk.
Yeah, that's the real hack, has a person given a talk.
Because sometimes there are 15-minute talks that will summarize the story for you, and that's really like getting it from the horse's mouth.
Or, Blue Sky tutorials where they published 18 posts about.
So a quick Google of the title, I think, is a good place to start.
Do we have anything else to cover? I guess going out on our format.
So you're the picker. Do you want to explain for ASIA broadly in the world why?
Just before that, because sometimes you have such good things about this. If you could have added one thing to this paper, what would it be?
I mean, I wonder what it's going to look like when it's out for real. Like a good edit would be helpful to really like tighten up the...
I think it's going to look the same.
Yeah. I mean, I think they might change monotonous to monotonic.
Yeah, that would be nice. Maybe they'll hear this before it goes out and they'll try to... But you can't move up the figures too much. My paper was accepted to Science Advances, and they said, if you change the content in any real way... then this will go back out for review.
You can't change the content. You can sneak in these kinds of, like I've done at the proof stage, I've found like typos that are not within the scope that they request, and I've made them, and it's been fine. Like they know what the limit is. If you're changing transformating into transforming, like.
I think if I could have added one thing to this paper, it would have been to put in other or images, and they might be in the supplementary because they say that there's a lot of things in the supplementary.
Yeah.
Images of other small metabolites, and specifically an image of something similar to oxygen where it's nonpolar and extremely small. And that's really what I want, is something that's nonpolar and extremely small, and I want to see how that's distributed.
Yeah.
Broadly in the world, why did your parents care? Your dad cared a lot about oxygen depletion and oxygen concentrations because oxygen oxygen is pretty parsimonious with energy in biology. And one of the ways I thought that I could mix, like, the beauty of physics with the beauty of biology in a new way that other people weren't doing is to think about my favorite tool in physics, which is energy minimization and energy considerations. That's really what I think is the most beautiful thing that's been created in physics. And in order to do that, I need a lot of information about energy in biology. And so this has kind of become, it was originally supposed to be a stepping stone, these considerations of energy in biology. It was supposed to be a stepping stone to like some biophysics where I consider energy and I consider the biological system and I make something beautiful out of that. But I've become fascinated with the shape of the stone, which is energy metabolism, which means oxygen, ATP, mitochondria. And so this one is about oxygen. And I also broadly cared about this because one of the great joys of being, there's a lot of tremendously difficult things about being a scientist married to another scientist. The scientific community says that they support it, but really do not support it. And it's tremendously painful. One of the great joys that you get out of it is you get to talk about things that are really important to you and that you really love with each other in a way that, like, I think most people don't get to talk to their best friends this way. They don't get to talk to their significant others this way. It's a very rare kind of intellectual relationship that's deeply rewarding. And so this paper covered an intersection between me and Linnea that allows us to think about what could we do at 10 p.m. on a night where we want to understand how the world works, where we could do it together. And those projects are not super common these days because there has been a bit of a divide and conquer between us of like Linnea is going to take on the problems of like resource scarcity in the world, and I'm going to take on problems of like the human condition in the world, and we'll meet up back together 60 years from now in a totally idyllic world. And so this was a paper that not just brought together my interest in oxygen and thus energy, but also my interest in doing things with Linnea, and that's why we broadly cared. It's interesting. We essentially picked this. We asked this question twice. At the beginning, we asked, why did you pick this paper?
Yeah.
And at the end, we do an outro for Asya.
Yeah.
But it's like, the first time, it's like, why did you pick this paper? Short version for the listeners. And the last one, it's like an emotional appeal to why we picked this paper. I don't know. It's a weird outro to do, but
that's what we've settled on for now. We can iterate.
I feel like the outro does not matter. Because nobody ever listens to a podcast all the way to the last word.
Yeah.
Like, even for podcasts that I love, that I listen to every week, I'm not listening to the last word. I'm usually piecing out like 5 minutes before the end.
I'm listening to our favorite podcast, like front to back. And they have compiled it all into one giant YouTube video. And so there, I do listen to the last words because it just is going to run into the next episode. And that's what I want anyways. But yeah, I agree. Also, if people are listening up till this point, they are diehards.
Okay, on that note, thanks for listening. Go read the paper and let us know your opinions. Do you believe that there is oxygen depletion in these biomolecular condensates in vitro? Let us know.
And see you next week.
Bye.